Welcome to this explainer. Today we're tackling a super fascinating everyday occurrence, exactly how a projectile reaches its maximum height. We're going to take this concept all the way from a totally real-world scenario, like just kicking a ball across a field, to a concrete mathematical calculation that lets us predict exactly where it's going to go.
Here is our roadmap for today. We'll start by defining the highest point, move into breaking down the velocities, derive the height equation, and then wrap it all up by calculating a real example.
All right, let's jump right into section 1, defining the highest point and the anatomy of a projectile's arc.
Picture this. You're on a field and a ball is kicked into the air. Let's say it's launched with an initial velocity of 50 meters per second, right, at a 30-degree angle to the ground. Our core mystery for today is simply this. How do we predict the exact peak of a thrown object? Like, how high will that ball actually go before gravity finally wins that tug of war and pulls it back down to Earth? Now, before we even think about touching the math, we've got to establish what we're actually measuring here. The maximum height is simply the absolute highest vertical position the ball reaches from the ground or its point of projection. It's literally the very top of that curved path. From this exact point onward, the ball stops going up and starts falling down.
What's really cool is how dividing this continuous curving motion into 3 distinct points makes it incredibly easy to analyze. We've got point P, which is our initial launch point right off the ground. Then there's point Q, the absolute star of our show today, the maximum height and the peak of the arc. And finally, point R is where the projectile comes crashing back down. So, to figure out maximum height, our entire focus just needs to be on that journey from point P straight up to point Q.
Which brings us perfectly to section 2. Breaking down the velocities, separating the x and y.
To figure out how that ball actually reaches its peak, we have to look at the invisible vectors driving it. Because when an object is moving at an angle, it's actually doing 2 completely different things at the exact same time. And to make sense of it, we have to completely separate those motions. On one side, we have the horizontal velocity, represented mathematically as u cosine theta. This is the push moving the ball forward across the field. On the totally flip side, we have the vertical velocity, represented as u sine theta. This is the component driving the ball upward toward the peak. Treating these as independent motions, well, that is the ultimate secret to unlocking projectile motion. So here's the absolute game changer. What happens right at point Q, our maximum height? Well, right at the very tip top of its arc, the ball actually hangs in the air vertically for a tiny, tiny fraction of a second. Its vertical speed becomes exactly 0. The upward momentum has totally run out. But remember, the horizontal velocity is not 0. It's still moving forward, which is exactly why it continues its arc toward point R instead of just dropping straight down like a rock.
Let's put this into practice in section 3, deriving the height equation, building the math step by step. To build our equation, remember, we only care about the vertical motion from point P to point Q. Step 1, we identify our initial vertical speed at launch, which we know is u sine theta. Step 2, we note the final vertical speed right at the peak, which we just established is 0 meters per second. And step 3, we apply the constant downward acceleration of gravity, represented as negative g, because it's pulling in the exact opposite direction of our upward motion. Take those 3 pieces, and we can plug them right into our standard equations of motion. After we plug those values in and do a little bit of algebra to isolate the displacement, which in this case is our height, the negative signs neatly cancel out. And we are left with this beautiful, clean formula. Maximum height, or h, equals the initial velocity squared times sine squared theta, all divided by 2 times gravity. Now, if you look closely at this equation, it reveals something truly elegant. Because gravity is just a constant pull, this math shows us that the highest point relies entirely on just 2 initial factors that we control. First, the initial velocity, u, meaning literally how hard the object is launched, and second, the angle, theta, the trajectory angle of that launch. If you know those 2 things, you know exactly how high your projectile is going to go. All right, it is time for the payoff in section 4, calculating a real example, putting the equation to the test. Let's lay out the known suspects from that initial scenario we imagined earlier. We've got an initial velocity, u, of 50 meters per second. We have a launch angle, theta, of 30 degrees. And of course, we can't forget the constant downward pull of gravity, g, which is 9.8 meters per second squared. So we take our shiny new equation and we drop those numbers right in. 50 squared times the sine of 30 degrees squared, all divided by 2 times 9.8. When we run all those numbers through, we discover that the ball reaches an exact maximum peak of 31.9 meters in the air. Think about that.
We just took a real-world chaotic action and perfectly mapped its physical limits.
As we wrap up this explainer, I'm going to leave you with something to ponder. We just saw that a 30-degree angle gets us to 31.9 meters. But looking back at our equation, we know that the angle literally dictates everything. So based on the math we just built together, how would changing that launch angle completely reshape our result? If we kept the exact same kicking force, but changed the angle to 60 degrees instead, how high would it go then? Give that math a try and keep exploring.